we're going to be in chapter 2, section 3 to start out with. This is all about measuring data. Now, it starts out with two vocabulary terms, I guess we'll call them. So accuracy and precision. So what does it mean to be accurate? What does it mean to be accurate? There's a lovely sentence in the book.
The first that one, where accuracy.
Okay. Basically, did you get it right? Okay. Now, if we look at this piece of copper right here, okay? Now, we measured this before in class, and we came up with a value of 45 grams, if I remember correctly, okay? So if we measured 45 grams, but in actuality, this was 53.2 grams. Is that an accurate measurement? If we measured 45.0 grams, but the true mass is 53.2 grams, were we accurate? No. Yeah. Yes, you're overthinking it. Okay? You're overthinking it. Which, let me just stop right here and say, that happens a lot in chemistry. Okay? I have found that for a lot of people in chemistry, they want the answer to be more complicated than it is. Okay? Chemistry is complicated enough. We don't need to want it to be more complicated. Okay? So, no, that's not a particularly accurate measurement. Okay? And we'll get into how we can determine how accurate it is in just a second. Okay? Now, we've established, yeah, that's not the most accurate. But if we measure that again, we measure the mass. This time we get 44.9 grams, and then we do it again, we get 44.8 grams, and then we get 45.1 grams, okay? That is actually very precise work, because as we do it over and over and over, we're getting the same answer, okay? So precision is, can you do the same thing over and over and over? All right. Any of you play piano? One person? Wow. Well, you can probably still understand this analogy. So if you have to play the piano, there are specific keys that you have to hit to make the right sounds, right? Okay. If you can play a song over and over and over without making mistakes, that's precision. Okay, you're doing the same thing over and over and over. Okay. Now, ideally, in chemistry, we have both. Because if you only have one, it's not that great. So if you look on page 47 in the book, it has those archery targets. So it has an accurate measurement. So one arrow, dead center. Okay, that's accurate. That's what you're aiming for. All right. The next one says it's precise but not accurate. So we have a group of 3 arrows that are all very close, but they're way off to the side of the target. Okay. So the person who shot those arrows, they were able to get to the same spot over and over, but it's not the middle of the target where you want it. Okay. Ideally, we have accurate and precise. So 3 different arrows, all very close to the center. And then the last one is worst case scenario. It's not precise and it's not accurate. We have 3 arrows spread all around. They're not grouped together and they're nowhere close to the center. So like I said, ideally, you can get accurate and precise. It's hard to say which one is better to have on its own. It is good to have precision because that means you're doing a repeatable experiment, but something is throwing it off. And so now you have to figure out what's throwing it off. If you can get one good measurement, then that's great, but how do you know which one is the good measurement? So, okay. So how do we decide if it's a good measurement or not? Well, we have a couple equations here. These are on page 48. So the error equation, the error is really just how far off the accepted value are you, okay? So we take the experimental value, which let's go with this set of data here. So the experimental value, what we measured was 45 grams, okay? And then we subtract the accepted value. So our error ends up being minus 8.2. Okay. Does that make sense? We were 8.2 grams off the accepted value. Now here's the thing. Sometimes being 8.2 grams off the accepted value is a great measurement. Okay. If we were trying to measure the mass of this building, to get the mass of this building within 8 grams, that's pretty good. Okay. So we need to have some sort of idea of how much is this error affecting our measurement. And that's where the percent error comes in. Okay. So the percent error, still have our data there, even though I erased it. Okay. So percent error. Okay, so we take, and this is important, the absolute value of our error. So this is a negative value right here. But what happens when we take the absolute value? Have you gotten to that in your math classes? Yeah, it's always a positive. So if it's a positive number, it stays positive. If it's negative, it turns positive. It's the distance from 0. That's the absolute value. Okay. So we take the absolute value of the error, which remember is these vertical lines here. Okay. And then we have to divide it by the accepted value. And then it is a percentage, so we multiply by 100. So in this example, we take 8.2 and divide it by 53.2, which then that gives us a value of 15.4%. Okay, so we were off by 15%, which is quite a bit. Okay. Obviously, we want our percent error to be as small as possible. That's just the way it is. You want your measurement to match with the accepted value. Okay. There is an example problem that runs through that again. Does that make sense? Do you want to do another example problem?
You
You want to do another example problem? Okay, that's fine. Like I said, I would rather go slow and have you understand it than just burn through all the material and have you. So let's look at this example problem number 5. So we have student A. So using student A's density data in table 3, which is on the previous page, to calculate the percent error in each trial. Okay. Report your answers to 2 places after the decimal point. So we have our equation. So our percent error, remember, is the absolute value of the error divided by the accepted value times 100. Okay. So if we look at this data, okay, the accepted value, our accepted value is 1.59 grams per cubic centimeter. Okay. Now this is nice because in their table, they do the math for you and give you the errors. So for trial 1, okay, we know that the error is negative 0.05. So we have to take 0.05 divided by the accepted value, 1.59. Okay. Now, the nice thing about this one is that the units should cancel out, okay, because your error is in the same units as the accepted value. So when we write grams per cubic centimeter, they cancel out. Now, I will admit, if I know things are canceling out, sometimes I will get lazy and not write them. That's a bad example. It's better for you to write them and cancel them out because you know you're doing it right. But just so you know, every once in a while on the board, I may forget. And so we take that and we do that math, multiply by 100, okay? And we get a value of 3.14%. Right? We've taken the error, which was reported in the table, so that was given to us. We divide by the accepted value, turn it into a percentage like that. Trial 2. So what's the error in trial 2? Who can tell me what the error in trial 2 is? What is the error in trial? 0.01. Okay. 0.01 divided by 1.59. Okay, and when we do this math, we get 0.63%. Okay. Notice how that difference doesn't look like a ton, 0.05 to 0.01, but it's actually a significant amount of the accepted value. Okay. The smaller your accepted value is, the closer you have to get to it in order to be accurate. Okay. And then the last one, trial 3. So our error there is negative 0.02. It's the absolute value, so we'll get rid of that negative sign. Once again, divided by 1.59 grams per cubic centimeter times 100. And that turns into 1.26%. Okay. So once again, the whole point of percent error, it shows you how accurate your measurement was. Okay. Now, obviously, to have percent error, you have to know what the accepted value is. Okay? If you don't know what the accepted value is, you can't do this. Okay? So there has to be some sort of established, we know that it is this value. Otherwise, it doesn't work. So. All right. Now, this next part, I'm just going to tell you right now, it confuses some people. Okay. But I think the main reason why it confuses some people is because, like I said, they look at it and they think it needs to be complicated and confusing. Okay. So let's just slow down, okay, and make sure that everyone is not going to get scared of this. Okay. Significant figures. Sometimes you'll hear me say significant digits, same thing. Book uses significant figures. I've had teachers that use significant digits a lot, and so that's just in my brain. It's the same thing. Okay? It's the same thing. So here's really what the problem is. So going back to measuring this, okay? Now, on the little electronic balance that we had, it said 45.0 grams. Now, does that mean it is 45.0000000 grams? Do we know all of those zeros? No, we don't. Okay. And in fact, most likely, those are not all zeros. So significant figures tells the people who are reading your measurements how precise you know this measurement. Okay? And so we have to figure out a way to determine how precise this measurement actually is. Okay? Because in chemistry, these are two very, very different numbers. In math class, that's exactly the same. Okay? But in chemistry, those are actually different numbers. This one represents a very, very high level of accuracy or precision. To get to 7 digits past the decimal, that's quite an accomplishment. Can it be done? Yes. but it takes some specialized equipment that we don't have access to. All right. So whenever you take a measurement, there is automatically some error in it. Because like we said, this was our reading, but we know that probably a lot of these were not actually zeros. Okay, so there's a little bit of error. And we need to figure out what do we know and what don't we know. Now, when you have an electronic device like the balance we used, it's pretty easy because it tells you, these are the numbers. Okay. When you don't, when you, let's say, of course I don't have it. What is this? Everyone's favorite class. Anyway, so here we have a line for 100 milliliters. Okay. But we actually don't have anything in between 100 and 150. Okay, so if the water line were in between those lines right here, we kind of have to guess. Okay, oh, that's about 130. Okay, and that's as precise as we could be. It's about 130. Kind of the same thing with this meter stick. Okay, if we were to measure something, comes to right here. Okay, well, I can say that's 17 centimeters, but probably maybe 17.2. Okay. Basically, when you have something with a bunch of lines on it like this, we call them gradations. Go to the smallest line that you can find, and then guess in between. Does that make sense? So if we were to be measuring something, so if we have this, and so let's say this is 1, 2, 3, and we probably have a half line, and those aren't exactly even, but we'll deal with that. Okay, so let's say what we're actually measuring goes to right there. Okay. We would say, so it's 1.4, so that line right there is 1.4. But we can see it's not exactly 1.4. So we would say it's 1.43. Okay. So when we do measurements in the lab, that is the technique that we'll use. Okay. That's just how you're supposed to do these analog measurements. That's one of the reasons why digital equipment is so nice, because it just gives you a readout, and that's what it is. So anyway, let's talk about how we determine what numbers are significant in a measurement and what are not. Okay. So let's say we have, well, let's just look at the rules first. Let's do that. So these are all on page 51, but we'll go over them individually. So to just recognize what is a significant figure and what is not, we have these 5 rules. Number 1 is great, because number 1, if it's not a 0, it is significant. Okay. So the only numbers that you actually have to worry about are zeros. Okay. You will be asked in a couple homework problems to determine, how many significant figures these numbers have. And right off the bat, if it is not zero, it is significant. So we just really need to determine which of these zeros are significant. So rule 2, final zeros to the right of the decimal are significant. So what does that mean? Well, if we go back to our 45.0, is that 0 on the right side of the decimal? Yeah, it's on the right side of the decimal. So that 0 right there is significant. Okay, according to rule number 2. Rule number 3. So a 0 in between two non-zero. Okay. So if we have 305, because that 0 is in between two non-zeros, it is significant. Okay. It is significant. And then 4 placeholder zeros are not significant. Basically, like if we have a number 0.00328, these are placeholders. Okay. If you can get rid of it by putting it in scientific notation, it's not significant. Okay. So placeholders are not. You can get rid of it by putting it in scientific notation, like we have here. So 3.28 times 10 to the minus third. Okay. You can get rid of it by putting it in scientific notation. It is not significant. Okay. And then the final one, counting numbers are infinite. So for example, if I look in this room, I can say there are 12 student desks. Okay. I absolutely know that I don't have a partial desk. Okay. There are 12 desks, there's no partials. So that technically 12, 0, 0, 0, 0, 0, 0, 0, 0, all the way out through infinity. Okay. So if you have counted a specific number of items, that actually has an infinite number of significant figures. Okay. So let's go through this and let's do some practice, because that's really how you're going to learn, doing practice. So if we look at this example, problem 6. So it gives us two numbers. So it gives us 0.00040230. Okay. So determine the number of significant figures. So we need to figure out how many significant figures are in this number. Well, first off, rule number one, non-zero is significant. So this one right here is significant. That is, and that is. Okay, that's easy. Now let's deal with the zeros. Final zeros to the right of a decimal. So we have a final zero right there. So that one is significant. Zero in between two non-zeros. This one. Are any of those significant? No, they're all placeholders. Okay. So this has 5 significant figures. Okay. Let's look at the next one. So the next one is that. So rule number one, non-zero. That one is significant, and that one is. Final zeros to the right of a decimal. Do we have a decimal in here? No, we don't. We have a zero in between two non-zeros. Okay. These ones turn out to be placeholders. Okay. When you don't have a decimal, then you just lose them. They're placeholders. Just be careful, because if we do this, all of a sudden, and I'm going to change this from non-zero to because that will address this one here. Because all of a sudden, this one becomes significant in rule 2, which then makes those 3 significant. Okay, but if you don't have a decimal, then only those 3 are. Okay. It takes a little bit of practice to get comfortable. But like I said, it really is just a matter of doing some practice. It's nothing that is overly complicated. None of these rules are, super long and drawn out and have multiple steps. You just, like I said, you need to get comfortable with them, which is going to take a little bit of practice. Okay. Let's move on. Depending on how we feel at the end, we may come back and do some more examples. But let's move to the next thing. So it talks about rounding. Okay. Now, when you do math with 2 measurements, okay, your calculator is going to give you as many digits as it can. Okay? That's how it's programmed. It's programmed to just give you as many digits as it can hold. But not all of those are actually going to be significant. Okay? So we need to figure out how to determine which ones are significant and which ones are not. And we round it there. Now, you guys know how to round, okay? If it's 5 or above, you round up. It's 4 or below, you round down, okay? You guys have been doing that for a long time. So really what we want to figure out is, how do we know where the cutoff for significant figures is? And it's going to sound more complicated than it is. Okay, so when I tell you the rules, just remember, it sounds complicated, but we're going to do some practices. We're going to show you what's going on so that we can get comfortable with this. Okay. So if you are adding or subtracting, okay, so adding or subtracting, the number with the fewest sig figs to the right of the decimal determines how many you can keep in your final answer. So here's an example. Well, actually, there's an example problem here. So we have 28.0 centimeters, and then we're adding 25.538 centimeters. And we're also adding 25.68 centimeters. Okay, so here's the rule. Do all your math before any rounding, okay? Do all your math before you do any rounding, all right? If you round too many times, it just introduces error. So we do this math, and we just put it in the calculator, 77.218. Okay, so now we have to decide where should we round this? What is the correct number of sig figs? Okay. And remember, the rule is the fewest to the right of the decimal. So which one of these numbers has the fewest digits to the right of the decimal? You say the very top one? Is that what you said? Good. That's the right answer. Okay. There's only one digit passed. Okay. What that means is that our answer can only go one digit past the decimal. Okay. So we have to round, and we get 77.2 centimeters. That we don't know. We don't know how accurate it is because we don't know that measurement there. Okay. So we can only keep that many digits. Okay. So, okay. And we'll do some more practice with that, but let's do multiplication and division. Now this one doesn't matter where the decimal is. So this one is determined by, correctly, fewest sig figs total. Okay. So we have another example problem on the next page. It's dealing with calculating volume. So of course, to calculate volume, you multiply 3 different measurements, the length, the width, and the height. So here we have 28.3 centimeters, 22.2 centimeters, and 3.65 centimeters. So when you put that in the calculator and just do that math, it gives you 2,293.149 cubic centimeters. But when we go back and look, how many significant figures are in this number? 3. How many in this number? 3. How many in this number? How many in this number? 7. 7 is too many.
Oh.
We're only allowed to have 3. Why? Because all of our measurements only have 3 significant features. So to say that this is that precise of a measurement is not true. Okay? We only know 3 significant figures. So we actually have to round this off after 3. So we have 1, 2, 3. Everything else has to be rounded off. So our final answer is 2,290. That's as precise as we know. All right? And at first that may bother you because, you know, like, well, but what about those extra 3 cubic centimeters that we measured? And you didn't actually measure them. Okay? With this level of precision, that's all we can do. Now, I want to stop here and mention, before moving on, if you take chemistry in college, most likely they will be very, very strict about significant figures. I've had classes where if you do all the math correct, but you report 2,293, that's wrong. Okay, and you get that answer wrong. I'm not that mean. Okay. If you give me 2,293, fine. Okay. I'm not going to be super strict, but you should try and round it to where it's supposed to be as much as possible. Don't give me all the numbers that you're calculating. Okay? Just try and get it close to what you feel is the correct number. Right? So, yeah, like I said, I'm not going to be super strict about, oh, that's the wrong number of significant figures and it's wrong. Even though technically is it wrong? Yes, according to chemistry, but we don't need to do it like that at this level. So, just let's keep it to kind of where we feel like it should be instead of yeah. So just like I said, don't give me every single number that your calculator gives you. Round it off. All right, let's do a little bit more practice with this, and then we'll set you free to do some homework. All right, so let's do some more addition and subtraction here. Let's look at, so we have 258.3 grams, 257.11 grams, and 253 kilograms. Okay. So we put that in our calculator. Remember, we don't do any rounding until we've done all the math. So 258.3 plus 257.11 plus 253. That gives us 768.41 kilograms. Is that the correct number of significant figures? Who says yes? Who says no? Who has no idea? Okay, well, this is addition and subtraction, right? So what is the rule for addition and subtraction? Okay, so it's determined by the one that has the fewest number of figures to the right of the decimal. So which one of these has the fewest number of digits to the right? The third one, yeah, doesn't have any. So that means our answer can't have any either. So our final answer has to be rounded off to 768 kilograms. Okay. Try some multiplication here. Let's see, so these are area problems. So we have 24 meters by 3.26 meters. So once again, let's put it in our calculator first. 4 times 3.26. That gives us 78.24 square meters. Is that the right number of significant figures? No. Where should we round it? 78, good. That number right there only has 2, so our answer can only have 2. Okay. Now, I will point out, like I said, you don't need a fancy calculator like this, but a calculator like this actually will do significant figures for you. I can tell this that I'm working in measurements, and it gives me the right number of significant figures automatically. So that's one nice feature about this. But like I said, I don't expect you to spend $100 on a graphing calculator. So anyway, so the last section is all about graphs. We will deal with some graphs in this class, but we're not going to take the time to talk about them. You will have learned a fair amount of graphs in your math classes. So yeah. Anyway, we'll stop here for the day, and I'll let you get started on your homework.